Three electric charges are arranged on an xy coordinate system as shown. Express all algebraic answers to the following parts in terms of capital Q, lowercase q, the distance x, the distance d, and fundamental constants. Part A. On the diagram, draw vectors representing the forces F1 and F2 exerted on the plus q charge by the plus q and minus q charges, respectively. So F1 is the force on this charge from this charge. Well, they're both positive, so it's going to be a repulsive force. It's going to point out that way. So something like this. And then F2 is from the minus q charge on this. So they're opposite signs, so they're going to attract, so it's going to pull this way. Well, more like that. Something like that. Part B. Determine the magnitude and direction of the total electric force on the plus q charge. So, I guess we're doing part B now. The first thing we can see is that the horizontal parts cancel out. So if we let F is the total force, I just don't feel like writing net at the moment, then Fx equals 0. And then if we think of that this having a component F1y, then we can see that Fy is going to be F1y plus F2y. But because of they are the same distance away, in other words, whatever this distance is, in fact, I'm going to call that distance, I'm going to give it a name, which I'm going to call it L. Then, since they're both a distance L away, and they have the same magnitude charges, we know that F1 equals F2. So F1y equals F2y. This means that Fy is really F1y plus itself, or 2 of F1y. But F1y is, of course, just 2F1 times cosine of the angle. Which angle? Cosine of that angle, which is really cosine of this angle is why I care about it. But I can see that this angle and this angle are the same because of parallel lines cut by a traversal, essentially. Right, this line and this line cut by this traversal. What is that? Corresponding angles? Corresponding angles are equal. And that's useful because given this triangle, I can say that the cosine of theta is simply d over L. From Coulomb's law, we have that F1 is going to be k times the charge times the other charge over the distance squared. So now I have that Fy is 2 times k q little q over L squared times d over L, or 2k big Q little q d. What is L? Well, L is simply the square root. Right, if we go up here, we can say L is the square root of d squared plus x squared. It's the hypotenuse of that right triangle. So L cubed, which is what I end up having here, is now going to be d squared plus x squared square rooted, but then cubed. So we get something like that. And that is the force in the y direction, which is the total force. Part C says, find the electric field. And so in general, the electric field is the force divided by the charge. So we immediately see Ex is 0, since the force in the x direction was 0. And Ey, well, when we divide this expression by that charge, it just gets rid of that little q. And so we end up with 2k big Q d over d squared plus x squared quantity to the 3/2, which is not particularly pretty, but is also not particularly hard. Part D says, calculate the electric potential at the position of the plus Q charge due to the other two charges. All right, well, the potential due to one point charge, or really a pair of point charges, is K times the one charge over the other charge times the other charge over the distance, which for us means that we have the potential due to the positive Q charge is simply that, Q over, well, what we called L. And then for the negative charge, it's the same idea, but of course we'd have minus Q, and over the distance separating it, but that's also L. And then the very happy thing about potentials is that the actual potential is just the sum of these two potentials, because the electric fields add. And so the calculation due to compute the potentials will just add as well. And then we get something either curious or annoying, depending on your point of view. Since those potentials are equal except opposite in sign, the actual potential at that point is 0. Part E, charge plus Q is now moved along the positive x-axis to a very large distance away from the other two charges. The magnitude of the force on the plus Q charge at this large distance now varies as 1 over x cubed. Explain why this happens. And the rubric here made clear they meant explain mathematically, but we'll also try and explain at least a little physically. The key thing is that as x gets larger, we see that L becomes like x. In other words, d squared plus x squared to the 3/2. Well, I'm going to factor out, it's going to be a little weird, but I'm going to factor out x squared from that, and I have d squared over x squared plus 1 to the 3/2. X squared to the 3/2 is x cubed, and now I have 1 plus d over x squared to the 3/2, but this is going to head towards 0. And so this whole thing heads to 1, and so we end up with just x cubed. So if we go back up to our formula up here, we have k, big Q, little q, d, but this has just become basically x cubed. All right, that's the mathematical sense, is that the separation is not very big compared to the vertical separation compared to how far we are. So it doesn't play much role, but then it contributes a little bit. Okay, physically what we have here is what's called a dipole, a positive and negative charge separated by some small amount but of equal magnitude. And the idea is that as we get further and further out, these things are acting as more and more as if they were at the center. If they weren't both at the center, of course, the actual electric field and therefore the force would be 0 because they'd have canceled out. But they're a little offset, and it turns out the little offset changes the power from being 1 over r squared to being 1 over r cubed. That's the physical origin of it, that they almost but not entirely cancel each other. Not entirely because they're a little bit shifted from each other.